talked about inverters. So, till now we assumed that inverter switching, the top switch and the bottom switch on and switch offs are instantaneous. So, but most of the time, not all the time, these semiconductor switches will have finite turn on and turn off time. So, we have to appropriately get the gate pulses, especially in a leg or in a pole, the top and bottom devices, such that there should not be any short circuit through the DC link. So, for example, in this figure, say one leg is shown here. So, let us say S1 is turned on. Now, due to PWM action, when S1 is turned off, we will be immediately turning on S2. So, let us take a condition where S1 and S2 has finite turn on and turn off time. That is a practical condition. So, even though S1 gate pulse is removed, S1 will take some finite time to turn on. Now, the moment if S2 is given, S2 will, before S1 turns off, S2 will turn on. So, what happens? There is a short circuit and heavy short circuit current will flow. So, to take care of that one, in a pole or in a leg, whenever a device is turned off and when the next device is turned on, there is a delay time between the turn on and the turn off and the next turn on device is given. This is called dead time. So, it has effect on the output. So, we will study that that effect in this class. So, effect of switching lag times. That means switchings are not instantaneous, there is a lag is there is a dead time is there. We are going to study effect of switching lag times. Switching time lag. Okay. So, as written here, there is a finite time needed for the inverter to switch on and off. That is what I explained before. This is turned on. Now, once the gate pulse is removed, this will turn off. But according to our so far assumption, immediately we will be turning on this one. So, before, if we turn on this one, before this is turned off, there will be a short circuit in the limb. So, we have to give a delay, that time before a switch. Before a switch in a leg is turned on. Before a switch in a leg is turned on. So, what happens? S1 is on. When S1 is on, see, depending on the current direction, even though the gate pulse is given, depending on the current direction, if the current is positive, let us say current is in this direction, S1 is on, then the transistor or the power device will be conducting. Now, but for an inverter operation, this current can be negative also. So, in the negative case, current will be flowing through diode. Okay. But diode, the moment it is reverse bias or the current is removed, it will quickly switch off. But the devices, transistors or MOSFETs, it require more or some more time to turn on and turn off. So, when S1 is on, in this case, current is flowing through the transistor. Now, S1 is off. As I told before, S1 is off. Now, we are giving a switching lag time. So, S2, that is S2 is turned on after some time. But in this case, because the current is negative, when the S2 is turned on, the device, the transistor is not conducting here the diode D2 will be conducting. Diode 2, D2 will be conducting. Here it is D1. Okay. So, in this case, instantaneously, the moment this is turned on, the current will through IA start decreasing, but current cannot change instantaneously. So, this load current will force it to come through diode. So, in this case, the switching lag switching that time will not have effect, because diode will conduct immediately irrespective of whether transistor is turned on or not. Okay. But if you see, let us take a case. Now transistor is turned on. Okay, even though diode is conducting, if you give instantaneously the transistor gate pulse, if you give it, see, it can turn on immediately. Before it is turned off, there can be a short circuit. So we have to give, even though diode is conducting or transistor is conducting, we have to give a finite turn on time, finite delay before the incoming device is turned on. So let us study the effect of this one. Again we will draw the switching circuit. Let us take the one limb or one leg. This is VDC by 2, VDC by 2. This is the diode. Okay, this is A. Let the current direction is like this. Let us say the ideal switching time, that is so far we concerned instantaneous turn on and turn off. See, let the ideal switching time is like this. S1 is turned on. S1 is turned on. So, if the switchings are instantaneous, this is S1, switch S1, that is S1, this is S2. Okay. If the ideal switching during S1 is turned on, S1 on, during this period S2 will be off. So, off we will represent as a negative pulse like this. Okay. At this point only S2 is on. So, S1 on, S2 off. If you see, the switchings are instantaneous, but what we said, we will give a delay. So, instead of turning on here, we will give a delay of, let us say, delay of TD. So, we will mark with a, so let us say the delay. So, it depends on the device. Okay, let us say for thyristors, it will require converter gate thyristors require large time. Okay, 30 to 40 microsecond. But for a presented IGBT or power transistors, you will get few microseconds. So, but still, when the PWM switching, it can affect on the output. So, we will study the effect of that one. So, we will give a delay and then turn on. So, this is the delay we are giving. Instead of turning on here, S1 is turned on. S1 is on. After the delay, this delay we will mark as TD. Okay. Similar way, this, when here at this point we have to turn, S1 is turned off and S2 is turning on here. But here also S2 turning on, we are delaying by this much, again TD. So, simultaneous turn on and turn off of device is avoided. So, this can avoid the short circuit, DC link short circuit. Here also we are giving a dead time of TD. So, this will take care of that too. But what will happen to the output voltage waveform? Let us say S2 is, till this point S2 is turned on, that is S2 is on, S2 on. Now, according to this current direction, this point, till this point D2 will be conducting, S2 is on and D2 is conducting, D2 is on. Okay. Now, what is the current direction? Current direction, this is direction we are taking positive. Now, we want to turn on S on. So, we will remove the gate pulse here, but even though the gate pulse is removed here, S2 diode will be conducting. Now, diode will be conducting, after some time only we will be turning on S1. So, what you say, previously we want the output voltage to go like this. If you say the VAN or VA0, this is our VA0. VA0 should have gone high here, but because of the delay, it has gone high here only. Okay. Again, when at this point, when S1 is off, immediately diode will conduct, that is instantaneous. So, if you see here, for the pole voltage, this much area is lost due to the dead time. This much area is lost, correct? But since the diode, whenever the diode conducting, the conductions are instantaneous, that time even the dead time will not have effect. But whenever the switching device, active device is instead of diodes, the transistor conducts, because of the delay, this much area is lost. Okay. Now, till this period D2 will be conducting, till this period, this period D2 will be conducting, D2 is on. Okay, this much area is lost. Area VA0, this is VA0, area lost for VA0. So, this will say this condition when I is positive, that is greater than 0, according to this connection. Now, when I is negative, negative means this is positive, this current will be in this direction, negative. Let us say in that case what happens? In that case, D2 will be conducting. When S2 is on, the transistor will be conducting, not D2, transistor will be conducting. So, the moment gate pulse is removed, immediately D1 will be conducting. So, that time will not have effect. Let us see now, I is less than 0. This condition we will say I is greater than 0. Now, let us take the condition I is less than 0. This we will draw with a different color. Now, current is negative, so the direction we will put it like this. Current is moving in this direction, I. So, this condition will represent as I is negative, I is less than 0. Then what happens? Let us take here, again according to the same switching here, when current is less than, at this point, what happens? Till this point, current is negative means transistor is conducting here. So, here again we will draw the pattern so that it will be clear. So, till this period, what is conducting? Transistor is conducting, that is this one, transistor. This is transistor 1 or transistor 2. transistor 2 is conducting, 2 is on. Okay. Now, the moment the transistor is removed, S1 is down. So, VA0 will be here, VA0 will immediately go high, and so till this point we are turning on S2. See, current is less than negative, T2 will be conducting. Okay. At this point, the transistor is off. Here, at this point, transistor 2 is off. So, what happened? Transistor is off, but current cannot change instantaneously. So, diode will immediately conduct. So, from here to here, D1 will be conducting. At this point, what we will do? Transistor 1 is off. Okay. But since D1 is conducting, transistor turn on, turn off will not have effect. So, D1 will continues to conduct till this TD period. So, here also D1 is on. Now, when T2 is on at this point, here, this is at this point, TR2 on. At this point, when TR2 is on, D1, the current will be transferred from here to the TR2. So, from here onwards, TR2 is conducting, TR2 on. So, if you see here, when the D1 is conducting, because of the dead time, the VS0, this much area is gained. Area gained, that is volt second, area gained for VS0. So, what happened? It can affect the fundamental. How it can affect? Let us go to the next page. So, what we studied so far, what we got the information now, due to dead time, the pole voltage, that means due to dead time, sorry, so what we are, due to that time, there is a change in area, that means volt a second in the pole voltages. So, how it can affect? What is the area of each pulse? Let us say the area of each pulse. That is delta E is equal to TD, that is the dead time, into VDC by 2. Okay. Okay. This TD may be in 5 to less than a microsecond. Usually TD, let us say TD less than 5 microsecond. So, we may think that it is negligible. But let us take a PWM operation. During PWM operation, Maybe 6-step operation it is okay, but during PWM operation, the number of cycles, the number of pulses in a half cycle of fundamental period depends on the triangular period or the carrier period or the carrier period. That means the number of pulses, let us say the number of pulses NP in a half fundamental period is equal to, half fundamental period is the modulating wave. So, Tm by 2 divided by the carrier period. This is NP, number of pulses. Okay. And this number of pulses, if you see here, due to carrier period, whenever the sign touches the triangle, you have these type of pulses, small pulses. So, these type of pulses, so if you say half period, you can see lot of pulses together, and if you see, it will look like a rectangular waveform. So, this can be approximated as a, the whole thing approximately equivalent to a square pulse like this. So, let us find out the area of the pulses. Area of the pulses, the height see these pulses we can approximate to a rectangular pulse of height h, and this period is equal to Tm by 2, that is Tm by 2. So, what is the area? H into Tm by 2 is equal to number of pulses into VDC by 2 into TD. It's a rectangle approximate. This is the total area in a half cycle, okay, because of the number of pulses. These are equivalent to a, we are equating to a square pulse or rectangular pulse of height h into Tm by 2, okay. So, what is h? H is equal to NP, okay, into VDC divided by Tm into TD, okay. So, what happened? So, dead time effect, due to dead time effect, TD in a half cycle fundamental period an effect of a rectangular pulse with height equal to H is appearing at the output voltage. Output VS0, pole voltage. Pole voltage. Even though we have used sine triangle PWM for nearly sinusoidal average variation, now there is an effect of rectangular pulse. Let us see how this affects. This also depends on the current error direction. So, let us see how this effect happens. So, let us study the effect of this dead time effect now. Let us see, this is our reference current, and this is our load current, and this is our x axis. So, this is our I load. Okay. Now, the reference waveform, the actual current, actual waveform what we want from the PWM modulation is, let this be this one. So, this is the waveform what we want. So, between the current and the voltage there is a phase difference of phi. This is our modulating waveform what we want, VM from PWM. Okay. This is from the PWM operation what we want. Now, let us see the rectangular pulse due to the dead time effect. So, if you see here with the current, I will draw it here according to the current direction, that is current is negative, as I told, we have a increase in the effect. So, there is an increase, we are approximating with a so this is this also this effect of this is the effect of that type. So, if you see when the current is negative, there is a increase in the pole voltage waveform. When the current is negative, current is positive, there is a decrease in the pole voltage waveform. So, what we get instead of the V reference, this also get added to this one. So, if you add this one, the waveform will be approximately like this. That is here suddenly there is a decrease, again there is an increase here. So, this goes like this. So, there is a distortion in the output VA0. So, if you say this is the VM plus our this waveform, you will say delta V, effect of that time. So, now the new fundamental waveform, if you see here, new fundamental waveform is here approximately. So, there is a shift in the fundamental waveform. If you see here, what is the shift? Shift is this phi dash. This is phi dash. So, we are adding a rectangular pulse. Now, apart from the fundamental, due to the effect of rectangular pulse, it will also contain fifth, seventh, low order harmonics. So, even though we are using sine triangle PWM with a large carrier frequency and dead time effect. If the dead time is very large, it can introduce fifth and seventh effect, and the current waveform instead of sinusoidal, it will be distorted with the effect of fifth and seventh visible in the current waveform. So many applications people think we can give large dead time so that the short circuit is safe, but this is a problem here. So let us like the phasor diagram. Phasor diagram, how it looks. We can draw the phasor diagram here. Let us see, this is our reference VM. Okay. Now our I load, this is our phi from this figure. Now according to this one, the fundamental component of this one is exactly opposite to the current component of this one. The fundamental component of this one will be approximately here. This is fundamental of delta V. So exactly opposite. So that means exactly here it will comes. So fundamental we will take it as delta V1, this one. So what happens? The net V reference, next modulating waveform Vm dash will be here. So this is our new Vm dash, that is exactly this waveform, new Vm dash. So this has to be Vm dash. This is our new Vm dash, and the new angle will be phi dash. Okay. So with the various load operation as IL, let us say IL varies, then this can go like this. So let us say unity power factor, then IL will exactly come here along with the Vm. Then what happens? The net Vm dash get reduced. Okay. When Im is in this direction, that is with the unity power factor, it is regeneration, opposite side, then the Vm will increase. So what happens? Even though we are operating the system for a particular modulation index, we will not be getting the correct modulation index. So it can affect, it can get output waveform can get distorted. So what it shows, the delta V1, we can say 4 pi into h height, that is equal to 4 by pi into Np into Vdc by Tm into Td. That time is the fundamental of the equivalent square wave, rectangular wave. That is equal to 4 by pi Tm by 2 divided by Tc into Vdc divided by Tm into Td, because we know Np is equal to Tm by Tc. Okay. This is equal to 2 by pi. What is Tm2 by Tc? This we can approximately write Fc into Vd into Td. Fc is the carrier frequency. So what it shows? it shows delta V1 increases with Fc for a fixed dead time. This will decrease the available upper modulation index. Upper or the maximum modulation index. So, what is the effect? As the modulation index M decreases, the output voltage, the output fundamental can reach 0 before M comes to 0. That means the relation between the modulation index, that is the sine triangle PWM, that is output is proportional to our modulating wave, is lost here. Also, because of the equivalent rectangular wave introduced, due to that time, the output current contains the low order harmonics such as fifth and seventh. So, even though PWM waveform we are using high frequency PWM, output current get distorted. So, many high performance drive application, when we require near zero speed operation, so dead time effect has to be compensated. So, for dead time compensation, we require the direction of the current. So, a typical way to reduce this one, we can see in the next slide. So, let us say this is the actual gate signal to S1, that is the top switch S1. Okay, or S1 or S2, we can take any signal, because when it is 0, this is S2. So, this is S1, here it is S2. Now, with the that time, let us say the conventional logic signal to S2, that is B. Oh, sorry, this is not the actual signal, the gate signal to S1 with that time. Sorry, this is the gate signal to S1 with TD. Now, let us draw the gate signal to S2 with the TD. Okay. So, this is gate signal with the TD to S2, S2 signal with the TD. Okay. Now, what we can do, we will OR these logic signals, that is we will generate this one. Okay. The 0 line for the logic OR is like here. this signal is S1 over with S2. Okay. Now this signal let us delay by TD. That means here. So let us say this is A, this is B, this is C, this is D. So D is the C signal delayed by T. C signal delayed by TD. Signal, that is this one. The top signal is delayed by TD here. That means this is the one, TD. Now from this one, we will generate the actual signals for S1 positive, S1 gate pulse and S2 gate according to current is positive or negative. So let us say, I will say S1 positive is the signal when current is positive. So I will turn on the device here, actual signal I will generate here. This is the S1 positive. I would say positive, current is positive. Now what about S2? S2 current is positive, then S2 current is negative. This is S2 negative, then the current is negative. Then from the delayed signal, when S1 is negative, this is S1 negative. Now S2 positive, that is current is positive. So if you this is S2 positive. So if you see here, the output voltage, the gain, that time effect, the gain lost and gain removed, gain lost and gain, the volt second gain can be compensated like this. So the output voltage waveform will be VS0 will be like this. This is the actual output voltage waveform. This is the 0. That is VS0 with the TD, and compensation, that time compensation. And the actual signal without compensation, what we require, if you see here, it is like this. That is actual VS0. So actual VS0 and the compensated VS0, if you see, the areas are same, positive and negative areas are, but the waveform is slightly delayed by TD. That's okay. TD for a switching device is equal to around few microseconds. So that will not affect if you for a motor drive applications, this delay is very negligible. So, but here what we want, to achieve this one, we require to achieve the dead time compensation, okay, to achieve the dead time compensation, current sensing is needed. This is not a problem because most of the motor drive application current sensing is required. So, with the current direction, current polarity for current polarity, then depending on the current polarity, the signals, gate signal S1, S2, S1 negative, S2 positive, we can give based on the original signal with the dead time. So, the whole dead time is divided by TD only. So, this way a dead time compensation can be achieved. There are various techniques available. This one technique is possible to achieve the waveform and the current and voltage distortion output voltage during PWM operation with dead time can be compensated.